We're all excited. Or at least some of us are excited. Some of us are very excited to welcome Tommi Muller to give the last talk of this session. And Tommi Muller is from a student in Oxford, and he's going to talk about something about low temperatures and electrons and microscopy. So please take it away.
So what is Cryo-EM? It's a technique. So in the past, one needed to crystallize their sample of molecules in order to image them. And the breakthrough with Cryo-EM is that you don't need to do this crystallization process. So this breakthrough was acknowledged in the 2017 Nobel Prize. So because the molecule is not completely frozen in water, it's allowed to freely rotate in 3D space according to some rotation matrix Ri. So for example, if you have some Mickey Mouse looking molecule and you take lots of Cryo-EM images, you'll take projections of this molecule undergoing random rotations, and you'll get images that look like this. So the Cryo-EM problem is to recover and reconstruct the 3D structure of the molecule given just these 2D Cryo-EM images where the molecule is rotating and you don't know how it rotates as it's being imaged. So to recover the 3D structure of the molecule, it's enough to figure out what the unknown rotations associated to each of the images are. So let's set up the problem. You have a 3D electrostatic potential phi of the molecule. You have n Cryo-EM images, 2D images, and associated to each image is a rotation matrix in SO3, and these are unknowns, and you need to find them. So to solve the Cryo-EM problem, we're going to use an important fact, which is this Fourier slice theorem. So the Fourier slice theorem essentially states that Fourier transforms commute with projections. So let's look at the left-hand side. The left-hand side says if you take your molecule and take an image of it, meaning you project, you get this I, and then you take the Fourier transform of this projection, I hat. That is the same as if you, yes. Oh, so it's at any point in space, R3, it's a positive or negative charge. Yes, yeah. So yes, so this left-hand side is equal to the right-hand side. So that's if you took the Fourier transform of your potential phi hat and then projected onto the plane where z equals 0. So if you project and then take the Fourier transform, that's the same as taking the Fourier transform and projecting. So if we write out what the Fourier slice theorem says for image I and image J, so corresponding to rotation Ri and Rj, you get this pair of equations here. This pair of equations is simply just writing out what's inside this bracket here. And it's expressed in terms of the rows of the rotation matrix. So Ri has 3 rows, R1i, R2i, R3i. And what this term is the values that phi hat takes on the plane spanned by the first 2 rows of Ri. And similarly, the same thing for image J here. So if you want to visualize this, the right-hand side of the equation was 3D Fourier space. there's one plane of values for the phi hat, one plane of values here, that's the top quantity here, another plane of values here, that's for the second quantity, image J. And generically, the two planes are going to intersect along some line. If you take this line in 3D Fourier space and project it down onto the Fourier space of the image, that line will give rise to one line here in I hat I, and the same line will give rise to a line in I hat J. And we call these lines common lines for image I and image J. And they correspond to this single line in the intersection in 3D Fourier space. So yes, so if we write these common lines, so Aij will mean the common line between image I and image J in the coordinates of image I, and Ji will be the common line between I and J in the coordinates of image J. And what we're saying is that the Fourier slice theorem will give you that the Fourier transforms of the images will agree on those lines. So this is what is meant by common line. Now, one can actually explicitly compute what Aij's are. So in terms of the rotation matrices Ri and Rj and the rows, you can they will have this form, and you can see there's some kind of mixing between the rows of Ri and the rows of Rj. And what you can detect from common line images, from Cryo-EM images, are scalar multiples of Aij and Aji. So you know Aij and Aji up to separate scales, lambda ij and lambda ji. That's what can be detected from Cryo-EM images. And so the strategy to solve this Cryo-EM problem is to use the fact that these Aij's have this specific structure to try and untangle and recover these rotations. So if you were to place all of the problems, variables into a matrix, you'll get a common lines matrix. So it's a common lines matrix associated to rotations R1 up to Rn. It has size 2n by n. It's a block matrix with 2 by 1 blocks, and the positions at ij and ji are those vectors, but up to some scalar multiple. So that's on the off diagonal of the common lines matrix. On the diagonal is zeros, because if you set I equal to j here, you're going to cancel things and get 0. So that's what can be found from the images. When the lambda ij's are all equal to 1, this is what we call a pure common lines matrix. And the pure common lines matrix has many good properties. An important one is that if it arose from a generic set of rotations, then it uniquely determines the set of rotations that generated it, up to a single global rotation. So in other words, if you are given a pure common lines matrix, you would be able to uniquely find the rotation matrices associated to this pure common lines matrix up to a global rotation. So in other words, you can recover the 3D structure of the molecule up to a single rotation, and that's good enough. That's problem solved. So that's what we really want. If we can find this pure common lines matrix, we've solved this problem. So it's important to understand what properties it has. If your pure common lines matrix came from a generic set of rotations, one important property is that it has rank 3. And the rank 3 comes from really an observation that if you arrange all the Aij's with their known structure into this matrix form, then they have a factorization that looks like this. it's rank 3, and when the rotations are generic, this exhibits a full rank decomposition. And when written this way, it tells you that the pure common lines matrices can be obtained as the image of a polynomial map from SO3 to the n to the pure common lines matrices. In other words, the map psi parameterizes all pure common lines matrices. So that's very good now that we have this space of pure common lines matrices. So if we want to find more algebraic constraints that these matrices have to satisfy, we can just look at the closure of the image of psi. So one can do this. One can look at the closure of the image of psi, look at a simplest case possible, n equals 3 images. You can run this on Macaulay to do a primary decomposition. It will take 2 weeks long, and you will find 94 polynomials that define this primary decomposition. And most of the vast majority of them are quite horrendous. They're extremely complicated polynomials that's just unusable and takes 200 pages to write out. So it's crazy mess. However, there are a few that are tractable and that have a nice interpretation and that are actually manageable. And the first one is that for any n, not just n equals 3, for any n, a pure common lines matrix satisfies the condition that its entries opposite the diagonal have equal norm. So this gives you one set of quadratic constraints. Another set of quadratic constraints you can find for any n, again, are that certain 2x2 minors have to be equal. And those 2x2 minors are related by permuting the indices of the entries of the common lines matrix. So what we have so far is a rank 3 condition, a norm equation condition, and a determinant equation condition like this. And at this stage, it feels a bit disappointing and hopeless, because what about those other 89 equations? It seems like we've barely scratched the surface in terms of characterizing the pure common lines matrices. And the miracle is that to solve the Cryo-EM problem, you don't need all those 89 other horrible polynomials. You just need these 3 constraints, and that will be enough to recover the unknown rotations for any number of images n. And I'll prove this to you later, so we'll come back to this. So let's go back to the problem again. Oh, sorry, an example. So yeah, if you look at the case n equals 4, you have if you have a pure common lines matrix, it's written like this in block form, and we know so far that this matrix A has rank 3, and the 2 propositions give us 14 quadratic equations, one set of norm equations like this, and another set of determinant equations like this. Okay, so let's go back to the problem. So remember that from our images, we can only detect common lines up to scale. In other words, we can only detect a common lines matrix. And what we really want is to get rid of these lambda ij's. We want to cancel them out and rescale the blocks of the common lines matrix to get a pure common lines matrix. And once we have that, then we're good. So the strategy is to use our algebraic constraints and force them onto the common lines matrix we found in order to undo these scalings, lambda ij, through an optimization problem. And it's very, very straightforward. You have a problem here. A hat is the common lines matrix you find from the images. Here's the lambda ij's, the scales. Here's the matrix A. And we're just imposing that A has rank 3. So that's the one set of conditions, and the second set are these quadratic constraints that we found. So, unsurprisingly, it's a non-convex problem, but we can still try and solve it anyway. And we can do this in 2 steps. What we're first going to do is just enforce the rank 3 constraint. We're going to forget about the second condition and only care about this first one. And you can do this using a convex method called alternating direction method of multiplier, ADMM. What this does is it alternatingly solves for the scales lambda ij and the matrix A, and also projects onto the space of rank 3 matrices. So it's this alternating way of finding A. So when you run your ADMM, you're supposed to get a rank 3 matrix at the end. And then once you have your rank 3 matrix after ADMM, then we try and enforce these quadratic constraints. And these constraints are nice enough. They're homogeneous, but they're also separable in some sense that you can find kind of optimal row and column scalings so that these equations are met as best as possible. So what we do is we get our rank 3 matrix from ADMM and then alternatingly scale the rows and then the columns and then the rows and then the columns, satisfying these quadratic equations. So that's kind of, if you've seen Sinkhorn's algorithm from optimal transport theory, it's very analogous like this. And then at the end, we should have A, which is rank 3 and satisfies the quadratic constraints. So far, this looks very dodgy, very sketchy. It's a non-convex problem, and I've told you some sketchy way of trying to solve it. But I will show you that this is the right approach. It works in theory, and it will give us exactly what we want. So what have I promised so far? My first promise was that rank 3 and quadratic constraints are enough. You don't need a full characterization of this variety of pure common lines matrices. And the second promise I just made was that this seemingly dodgy way of solving the problem actually does work. So what's the approach? So you start with your common lines matrix B. It's scaled by it's made up of a pure common lines matrix A, whose entries have been scaled by these lambda ij's. That's your common lines matrix you get. Now suppose we run ADMM and modify B using ADMM and rescale all the entries of B so that it becomes rank 3. That's supposed to be the output of ADMM. If it has rank 3 and we're done, then the best thing happens. The final answer is only off by row and column scales. So meaning after you run ADMM on B, you are only off from the pure common lines matrix just by some row and some column scale. And that's exactly the situation you want to be in when you run Sinkhorn's algorithm, because Sinkhorn will remove those row and column scales and you get your pure common lines matrix. So after this, you run your ADMM and then you run Sinkhorn. What happens? In other words, what happens if B also satisfies the quadratic constraints? Then the final matrix B you get after doing these 2 steps is just some alpha scalar times the pure common lines matrix. So you're done. If you do these 2 sequential steps, you've found your pure common lines matrix up to scale. Are there any questions? Okay. So, oh yeah, okay. So this is a kind of a algebraic or algebraic geometric approach towards this Cryo-EM problem, which hasn't been studied before. And it's given us a new insight into this recovery problem. And one final remark is that the Cryo-EM problem actually is a more general instance of the synchronization problem, which is very much connected with Aaron's talk. And if I just quickly describe, it's this problem where you have a directed graph and a group, and you place group elements on the edges of the graph, and you want to ask how what group elements you need to place on the vertices so that the graph is globally consistent. In other words, if you have an edge and you take your group element on the source vertex times the group element on the edge, it should equal the group element you assigned on the target. So the Cryo-EM problem, the fundamental matrix problem, and many other problems are instances of synchronization. Now, thank you for listening.